All right, class, let's dig into this. So the material for today is angular kinematics. This is a little bit of a jump from the fluid stuff that we were working on, but in a couple of lectures we're going to bring it all back around and you're going to see the connection, I hope. Okay, so here's what's going on. The first thing to do is to kind of cast our minds back to linear kinematics, right? This is the stuff that we were working on at the very beginning of class, and you can see, let's say that there's this thing here, a little car, and it's got an acceleration 2 meters per second squared. You can see, here's its velocity changing. You can see its position changing. We had all these things going on, right? But this is linear kinematics, or kind of, you can think of it almost as like one-dimensional kinematics, where I'm moving just in the x-plane or maybe just in the y-plane. And we had all these equations and way of thinking about these things. So what we want to add to this, right? And here's our, beautiful equations of motion. What we want to add to this and what we want to think about today is, well, what if we spun everything? And I mean, because we might as well, right? We're getting close to the end here, so we might as well spin it up. Okay, so here's what I want you to think about. To beginning with, we've got the red dot and the blue dot, right? They're racing around this track. And the first thing I want you to think about is, right, describe the motion of the dot. What's the same about the dots? What's different about the dots? And as you're doing this, as you're thinking about this, you might look over here and say, well, it looks like, they're staying in line with each other. They're kind of moving around. So although, if this is happening, then the blue dot's probably going a little bit faster than the red dot because it has a bigger distance to cover in the same amount of time, right? If they're going to track together, right? If that's the start of the race and they're going around and then they finish at the same time, right? So this kind of gets us thinking about, well, what angle does the red dot move through in one revolution, right? They go through the same angle, right? 360 degrees in the same amount of time. So they have different velocities, but the same, well, I'm going to call it angular velocity, okay? So we're going to come back to these terms. We're going to be thinking about these dots quite a bit today. So, all right, so circumferences and angles. I've got two circles here, different radii. So, what is the circumference of each circle? Well, we have a basic equation that we learned in geometry to calculate that, right? That the circumference is equal to 2 pi times the radius. And this thing is like clicking through on its own. And so the kind of cool thing about this is that I can divide both sides of this by r, and I get this 2 pi left over. Okay, and I can do the same thing over here. I can divide by the big R, and I get this. I get the same thing over here. That there's this consistency between the two circles, even though the circumferences are different, the radii are different. It's like the circumference is being adjusted depending on what the radius is by this 2 pi. Okay, and so we want to think a little bit about what that might mean. Okay. So let's look at arc length, for example. So here's a line, and let's say that I rotate that line a certain amount, right? And if I look at a given radius here, and as we trace out that angle, that change, right, I get this little arc length, right? So if I have a point here at radius 1, and I swing it out, okay, it traces this little arc. We're going to call that arc length. And the symbol we're using for arc length is a little s, okay? So the question is like, how do things change, right? What is the arc length now if I'm 2 radii out, okay? And it turns out that it's just double the arc length, okay? Double that original arc length. 2 radius, double the arc length. So the same pattern holds, right? At 3 radii, I get 3 arc lengths. At 4 radii, I get 4 arc lengths. So we kind of want to think about like what's going on here. How could this be? Okay. And now one thing to note is that for every single one of these arc lengths, it's the same angle, right? I didn't change the angle that I opened the line at to get a bigger arc length, I just went out a little bit further distance and I get a greater and greater arc length. That's, by the way, right, if you're a racer or a runner, you try to get into that inside track as soon as you can, because if you're going around in circles, right, the smaller radius is going to give you a smaller arc length. So what does this tell us? That the angle is a ratio between the arc length and the radius, okay? And this ratio only works if we're thinking about the angle in terms of radians, okay? And this is kind of, by the way, where the radians comes from. You might think, well, why not just use degrees? Why not just have, my 360 degrees, for the full circle, or 90 degrees for a quarter of the circle? It's because of this principle, right? That the arc length that's traced out, if I divide that by the radius that I'm at, I get this number, and so we're calling this radians, right? Because it's based on the radius, right? That's where all these things are kind of coming from. Anyways, so if I need to calculate an arc length, okay? So we know the circumference of a circle, right? We established that a couple of slides ago. The circumference is 2 pi r, and so the question is that isn't this just the formula for arc length, right? Where the circumference is an arc length that's all the way around, right? That matches an angle of 360 degrees, right, at the full radius, okay? So if I replace the circumference with the arc length, and I replace the 2 pi, which is in radians, right? 2 pi, this puts me in this angle degree of radians. And then if I multiply by the radius, I get the arc length, right? So 2 pi, which is going to be the same as 360 degrees, times r is going to give me the circumference, or that arc length all the way around, okay? And we kind of see that here in this animation where this traces out, right? You can see, you can't see. Here's my radius, and it's 1 unit. Let's say that's a meter. And I notice when this gets all the way over here to 360 degrees, that's going to be just pi. Did you see how that was 3.14? Maybe you missed it. I mean, we can watch it again. It's just going to keep going and going and going. Here it comes. You're going to see when it gets all the way over here, we're going to get just pi. Yep, 3.14. Okay. Okay, so if we bring that back down to here, okay, notice for the same angle, okay, as I increase the radius to 2, that's just, if I multiply this by 2, then the arc length goes up by a factor of 2, right? Everything tracks. 4 radii gives me 4 of that original arc length. Okay, so what if theta was just 1 radian, okay? So at a radius of a meter, right, 1 times 1 is going to give me an arc length of 1 meter, right? And again, this is kind of where the definition of radian comes from, that if I have 1 meter long, gives me a 1 meter long arc length. So I'm going to call that an angle of 1, right, per that ratio. So then, of course, 2 meters is going to be an arc length of 2 meters. Okay, so it's going to be really important for us that we can convert between radians and degrees, right? A lot of the problems that we deal with, we may be thinking about, if I turn this through 200-degree turn, what arc length is that going to trace out? And I can't use the 200 degrees. I have to be able to convert that into radians, okay? So we have this thing, it's called the unit circle. And on the unit circle, here I'm at 0 degrees, and I'm at the point, the Cartesian coordinate 1, 0. If I rotate this out 30 degrees, that's the same as pi sixths. Or, you may be more familiar with that pi is the same thing as 180 degrees, right? All the way around, 0 is going to be 360 degrees and 2 pi. But I've got pi and 180 degrees. So, this may be a really important figure for you as you think about, well, 45 degrees is going to be pi fourths, 60 degrees is going to be pi thirds. And then it also, now we're not going to use these, but it also gives the Cartesian coordinates for each of these locations. but that's not going to be as important for us. We just want to think about, as I sweep this around, right, each of these angles in degrees is the same thing as a certain angle in radians, okay? So we're going to need to be able to convert, okay? So 2 pi radians is the same thing as 360 degrees, and we're going to use this conversion factor, right? Because I can, if I multiply something by 1, it doesn't change anything. So you may have 2 pi radians on top and 360 degrees on bottom, or 360 degrees on top and 2 pi radian on bottom to do those conversions. All right, so let's practice. How many radians in 90 degrees? There's a myriad of ways of doing this, right? You could look at your unit circle and pull it off of there, or you could use the conversion factor. So right, 90 degrees times 1, and I could just change this 1 into 2 pi over 360 degrees. Notice my degrees are going to cancel now. It's going to leave me in radians. This should be an RAD there. And just for fun, right, I can slide the 90 over here and bring the 2 pi over here, right? And 90 over 360, that's a fourth of the circle, right? Because right here, 90 over the full 360, that's a fourth of the unit circle. So it's the same thing as, 2 pi times a fourth, which just gives me pi halves, right? Or I could have just looked at the unit circle and seen that 90 degrees is pi halves. But most of the time, we're not going to have angles that land perfectly on the unit circle. So being able to do this conversion is going to be important, right? So 90 degrees is the same things as pi halves radians. Okay. All right. So what could a problem like this look like? So let's check it out. Let's say we have a big pulley, and we've wound a string around it a whole bunch of times. Okay. So a box is tied to the end of the string, and if I let go of this box, it's going to start to fall. It's going to start to unwind the string, right? This pulley is going to start to roll, okay? So a box is fastened to a string that is wrapped around a pulley of radius 4 meters, okay? The pulley turns an angle of 43 degrees, right? So this distance here that turns an angle of 43 degrees, well, how far does the box move, okay? And now the key thing here is that 43 degrees, if you think about it, the string is lying on top of here, so it's going to unwind just that same amount of string, right? So this distance the box drops is the same as the distance as this arc length from the 43 degrees, okay? So now, right, we can go back to our thinking of like if I have an angle, I can turn that into an arc length. I just need to get this degree thing out of degrees and into radians, right? So 43 degrees, I need the degrees to cancel, so 2 pi over 360 degrees. So my degrees will cancel, so I'm going to multiply by 2 pi, divide by 360, and I'm left with 0.75 radians is my angle in radians, okay? Now I can just go to my equation that the arc length is the angle in radians times the radius, and I'm going to get 3 meters. If I had tried to use 43 in the space of an angle, I'd get this gigantic number, and that should look ridiculous to you. Yeah. So that's how this works. That's what's going on. So this is like one way to think about this one kind of problem, right, where I can move between, some movement out here and the turning of a wheel. Okay. So. All right, here we go. So what can we now say about the dots? Okay, in terms of this equation, right? I know that they're sweeping out the same angle, right? So this angle is the same for all of them. And so the arc length that they're sweeping out is going to depend on their radius. So since blue has a bigger radius, it's going to have a bigger arc length, right? And we kind of saw this before, but we can now think about this in terms of our equation, okay? Now the big question is well, where do we go from here? Okay, we've talked about a displacement, right? We're moving these things, we're displacing them, right? They're here, they get displaced a certain angle or a certain arc length. You could think about that as, that's displacement. Well, what was the next topic we covered before, right? I have a thing, I want to move it, I need to get it from A to B. Well, these things have speeds. Okay, so that's kind of where we're going. So here we go. So, playing a record, I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right? Yeah. But the point on the record's edge has to make a bigger circle in the same time, so it goes faster. See? 2 points on one disk move at 2 speeds, even though they both make the same revolutions per minute. And this is how we spend the rest of our break. Okay, so angular and tangential velocity. Okay, and so if we're talking about in terms of their rate of movement, what is the same and what is different? Okay, and as you look at this, is the rate that the angle for red changes, is that different than the rate that blue's angle changes? No, right? Those are the same. Okay, those are the same. So, right, their angular velocities are the same. That's what we're going to call this. The rate at which the angle is changing, they're the same, even though they have different radii, right? They have these two things have the same angular velocity. But do they have the same, and we call this tangential velocity, right? So if we were to like put a speedometer on them, like the speed that they are moving at that movement, or so because they're moving tangent to some curve, like what is their instantaneous speed? Well, that is different, right? The rate at which the particle is moving tangent to the curve, and those things are different for both of these. The blue one's got to be a little bit faster to go around in the same amount of time that the red one does, okay? All right, so in this nightmare, notice we're tracking on, we've got a whole bunch of different dots. Yellow and blue have the same, and so by the way, this omega, that's angular velocity. They have the same angular velocity. So yellow and blue are changing angles at the same rate. Okay? But notice, do any of them have the same tangential velocity? And they don't. Hold up. Yeah, the yellow is down here. Green, blue, and they're all, wait. Oh, blue? Oh, check this out. Blue and red have the same tangential velocity, but different angular velocity. So they don't line up anymore, but the rate at which they're going around their tangent speed, if I had a speedometer on them, is the same. You can kind of see that, but that makes their angular velocities different because they're at different radii, right? So, I mean, there's a lot going on here. We could stare at this all day long. It is pretty cool, but we won't. Okay, so thinking about angular velocity, right? Angular velocity is the rate at which the angle is changing, and that's measured in radians per second. Again, we're not going to think about this as degrees. So the symbol for angular velocity is this omega. So it's the Greek symbol. Looks like a little W. Alpha and omega. And we are going to have an alpha, right? Omega is like the end of the alphabet. So there's omega. And our equation here is it's the rate at which the angle is changing, right? So omega is going to equal the change in the angle as measured in radians divided by the time, right? So just like velocity is the change in displacement over a change in time, angular velocity is the change in angular displacement, right? Is the change in the angle over the time, right? It's the rate at which the angle is changing. Okay, so here's a problem. Here we can try this out. So on a wristwatch, right, an old one, what is the angular velocity, the magnitude and direction? What does that tell you about these angular things? That they must be vectors as well. Okay, the magnitude and direction of the second hand on a watch. So if you think about that second hand as it goes around, does it matter how big the second hand is? No, it doesn't, right? Its radius doesn't matter because I only care about the rate at which the angle is changing. Okay, so if you think about that, right? Well, it's going to go 2 pi or a full 360 degrees all the way around 2 pi in 60 seconds. So that boils out to be about 0.1 radians per second is the angular velocity of a second hand, okay? But what direction, right? And so this is the thing we need to think about, right? What is the direction of that vector, okay? So finding, let's see, the concept of omega, finding a vector to describe a rotating wheel. So imagine we have this wheel that's spinning, and where am I going to put the vector, right? If this thing is turning, can I put the vector here? Well, no, because a few minutes later, right, if it's attached to this part of the wheel, it's going to turn down. Now it's going to be here, and then it's going to be here a little bit later. Okay, so I can't, right? I can't do that because it's constant. That would be constantly changing. So I can't try and put the vector on the edge of the wheel because it's constantly changing. Okay, so well, what if I put it just at the center, at the axle? Well, that's kind of turning as well, isn't it? That thing is spinning around as well. So I can't have that, right? Because the direction of that vector needs to hold true. So what we need is we need a new perspective, okay? And what we're going to do is, we're going to put the direction of that vector as an arrow that's sticking out of the axle, that's perpendicular to the plane of rotation. Ooh-wee. Okay? Perpendicular to the plane of rotation. Okay, so here's how you imagine this. And class, you got to do this with me, okay? So imagine that there's a disc and it's spinning just like you see. So what you're going to do is you're going to take your right hand, right? Okay, by the way, this is called the right hand rule. You have to, you might be left-handed, and I apologize, whoever built this construct built it for right-handed folks. So you just got to use your right hand. So you're going to stick your right hand in front of you, okay? And you're going to, so for this wheel, you're going to curl your fingers in the direction of the turn. You can kind of see that. Curl your fingers in the direction of the turn and stick your thumb up, right? So it's kind of like you're giving the screen a thumbs up. Your fingers are curling in the direction of the wheel, and your thumb sticks straight up, okay? That is going to be the direction of the omega vector. So the wheel is turning in a plane that is perpendicular to the vector, and that's always true, by the way. The wheel is turning in a plane that's perpendicular to the vector. And in this case, right, that vector is pointing up as the wheel turns, and you can see that on your right hand, okay? So if I flip it like this, so now the wheel's turning the other way, right? If I'm going to use my right hand, if I want to curl my fingers the other way, I have to turn my hand over. So now it's like I'm giving a thumbs down, and I curl my fingers that way. And so you can see that that vector is going to point down, okay? We will practice with the right hand rule more and more because this is going to be important for us, and it's going to be an important way to think about this. You know, you might just say, well, can't I just call this, so for example, like this one could be counterclockwise. Can that be the direction of the vector? And this one is clockwise. We're like, well, I mean, yeah, that is what we're doing, but I still need to assign counterclockwise isn't like an arrow direction. So the way that we assign an arrow to this is with the right hand rule, with a line, with an arrow that's perpendicular to the plane of rotation, okay? Okay, so what is wrong with this picture? So here I've got a rotating disc, and here's the hand, and I'm using the right hand rule. And by the way, this is a Copilot fail. I tried to get Copilot to make an animation of the right hand rule, and this is what it gave me. So yeah, first of all, that's not a right hand. That's a left hand, right? If you're looking at the screen, that's a left hand. So this is, by the way, if you're in the testing center during this exam and you see one of your peers, and if they've got their left hand up in the air curling their fingers, you know that they're doomed because it's the right hand rule, right? So first fail is that you're looking at a left hand. The other fail here is that the fingers are not curling with the disc. The disc is spinning as you're looking at the screen, it's spinning counterclockwise. So if I take my right hand and spin counterclockwise, my thumb's pointing straight at me, right? So if this is the disc and it's spinning like this, and I use my right hand, that vector should be pointing straight at me, and this is way not doing that. So a couple of big fails here with Copilot's attempt to animate that. All right. Okay, so we've gone over a little bit like how to think about and deal with direction, like that vector directionality. So okay, I mean, you can kind of see here where we're headed, right? We looked at, I've got angular displacement, and I have angular velocity, And so, of course, if I have an angular velocity, I can have an angular acceleration, right? That velocity can change. So that's what's going on here in this animation, is that I have all these dots, and now notice the red and blue dot, their angular acceleration is 0, so their angular speed is not, their angular velocity is not changing, but the green, oh, it just restarted. Do you see how they're going slow? The green and the yellow dots are going slow, right? They started out with pretty small omegas, but as this remains constant, over time, these omegas are going to get bigger and bigger and bigger. The green and the yellow dots are going to get going faster and faster and faster as they go around. And the other thing to notice is that as their omegas grow, what also is going to grow? Well, their tangential velocities are also going to grow, right? You can see the green one slowly ticking up and the yellow one even slower, right? And that's because they have different angular velocities. But these are what I would maybe call the tangential velocities, these V's out here. But you can see what's going on, and this is tracking, by the way, in radians, the number of angles they've swept out, right? And so these have gone around, quite a few times. Okay, so angular acceleration. Okay, so I need an operational definition of angular acceleration. And by the way, do you see how it's not an A? This is an alpha. Okay, so this is the beginning of the Greek alphabet, and omega is the end of the Greek alphabet. And by the way, we're going to add some more Greek letters here as we go along. Notice that this is also a vector. So a spinning wheel gradually slows. Find the vector delta omega. What is the change in omega? Okay. Well, okay, so here's omega initial, and I've drawn it as this vector. And so the length of this vector is going to represent the magnitude of the angular velocity. And this direction, does that mean it's spinning this way? Nope, right? If I were to do this, I'd stick my thumb in the direction of the arrow, and my fingers would curl in the direction of the disc or the wheel or whatever it is that's spinning. Right, so this is kind of spinning into the page on the bottom and out of the page on the top, like above it, right? Okay, but so if it's gradually slowing, right, then the omega is going to get shorter, still spinning in the same direction here. Okay, so here's the initial omega, here's the final. Well, what's the change in omega? Well, it's this thing, of course, right? So if I went from here to here, I have this vector that shows me what delta omega is. And that is going to be the same direction as alpha, right? Because alpha is going to be built off of delta omega, okay? So alpha is built off of delta omega. And the value of alpha is just how long did it take for that change to occur, right? So just like acceleration is the change in velocity over the change in time, alpha, or angular acceleration, is the change in the angular velocity over the change in time, okay? And one thing to kind of just keep in the back of your mind is that the direction of alpha is not necessarily given by the right-hand rule. There are ways you can use it to think about. You can use the right-hand rule to sometimes think about alpha, but you do need to be careful. So, for example, now this is a demo, the Wheel of Death, that we're going to do in class, and we've demoted it to the Wheel of Serious Injury. This one's probably, there's no nails involved on this one. But anyways, so imagine I have a spinning wheel, right? And I've got my omega. And by the way, if that's the direction of omega, right? If I stick my thumb in the direction of omega, I have to curl my fingers. That means that this wheel is spinning like this, right? If you're doing your right-hand rule correctly, the wheel is spinning like this, okay? And the question is, well, what happens if the omega vector doesn't get longer or shorter? What if it happens if it just changes direction? So what happens if all of a sudden omega is down here? Same length, same magnitude, but now it's down here. Well, if this is omega initial and that's omega final, well, where's delta omega? Okay, well, it's right there. And this is why the right-hand rule, you got to be careful with the right-hand rule and thinking about what direction alpha is going to be, because this is a little bit counterintuitive. We will do this demo in class, and so you can kind of see where this gets represented, but in this case, it's like alpha kind of points down a little bit. which would introduce a weird rotation into the system, which we actually can perceive. You do see that. But anyways, we'll run that in class. Okay, so here we go. More of the same. You throw a baseball straight up into the air with an initial velocity of 20 meters per second. How many seconds before it comes to stop at the top? Okay, so you look at this and you're like, oh, this is a kinematics problem. This is linear kinematics. I totally know how to do this, right? How would you go about tackling this problem? Well, of course, you're going to build a data table. And from that data table, you're going to say, okay, well, what variables am I looking for? What do I not have? What do I have? That's going to help you pick a kinematic equation. And then from that kinematic equation, you're going to solve for the time, right? And you could tackle this. Well, guess what, class? We're going to use the exact same strategy for thinking about rotational things, right? So I throw a ball straight up into the air with an initial velocity of 20 meters per second. I spin a wheel with an initial angular velocity of 20 radians per second. And if it has an alpha that's opposing that, how many seconds before it stops? It wouldn't be at the top, right? But eventually the wheel, that alpha, if it's acting against the omega, is going to bring the wheel to rest and start turning it the other way, right? So this is, we've kind of spun it so that it's on edge. And so I'm going to write it like this, right? So here's my angular initial velocity is going to be 4, so we're calling this 4 radians per second, okay? Okay, I'm in the right units. I'm in radians per second, 4 pi radians per second. Now, this little symbol here, by the way, is giving you the direction, okay? As you want to think about an arrow, right? If I shoot, so I've taken this arrow here, this little directional arrow, and I've spun this, so now that red arrow is pointing right at me, okay? And if you shoot an arrow at someone, then the thing coming at them is the point, right? So if I was doing the right-hand rule on this, I'd stick the thumb straight out of the page, right? Because it's pointing right at me, and I'd curl my fingers, okay? So the initial omega is this thing, okay? And, I could define alpha. Now it has to be opposing it, right? And so for into the page, we use an X, right? And so arrows, like an arrow you shoot at a target, is what's on the back of an arrow, where it's the fletchings, okay? So if an arrow is going away from me, right? So into the page is away from me, I see the fletchings, okay? So I see the point of the arrow if it's coming at me, I see the fletchings if it's going away from me, right? That's what this dot and this X, they're just giving you the direction. So the alpha is into the page, it's against the omega, and this thing has an alpha of pi radians per second squared, or radians per second, right? The rate at which the omega is changing. Okay, and then I could go through so how long before the wheel stops? Some of you are thinking, okay, well, I need a kinematic equation, and that's exactly what we're going to build, right? By the way, this one is 4 seconds, right? So here we go. So let's do some magic. Okay, so here's where we started at the beginning of the year. That acceleration is equal to the change in velocity over the change in time, right? And they're all vectors. And we also kind of are thinking about, okay, so well, alpha, by the same definition, is just the change in omega, right? The angular acceleration is just the change in the angular velocity over the change in time, okay? So in linear kinematics, I have these equations, right? These are my good friends. We know how to use these. We love these. Well, guess what? They exist in the angular space as well, right? I can translate all of these over to angular terms, right? But instead of V's and A's, I'm going to use omegas and alphas. Omegas and alphas. So the final angular velocity is equal to the initial angular velocity plus the angular acceleration times the time. Okay, same kinematic equation, but this one operates in the angular space where we're measuring changes in angle. Okay, here we go. Again, instead of delta x, instead of the change in position, this is going to be the change in angular position, right? The angular displacement. 1/2 the sum of the omegas times the time. Okay? And then I'm doing the same thing, right? Instead of x, I have theta. Instead of v, I have omega. Instead of a, I have alpha. Okay? All of my kinematic equations still exist in the angular space. So if you are really good at linear kinematics, you are going to crush this angular stuff. And if you needed a little bit of practice, well, now we've got some more time to practice. Here we go. So here's a sample problem. The drill bit of a variable speed electric drill has a constant angular acceleration of 2.5 radians per second squared. The initial angular speed of the bit is 5 radians per second. After 4 seconds, what is the bit's angular speed and what angle has the bit turned through? Okay, so after 4 seconds, angularly speaking, how fast is it going? And how many times has it gone around, right? What angle has the bit turned through? Okay, here we go. So, oh, my screen kind of cuts a little bit of the top of this off. The drill bit, and anyways, so the initial angular speed of the bit is 5 radians per second after 4 seconds. Class, how do we begin any kinematics problem? We build a table. We build a table, we build a table. Class, please put together these tables. They will save you. Okay, here we go. From the problem, I don't know what the angle, right? That's what I'm looking through. What angle does it turn through? It tells me what the angular velocity is to begin with. I don't know what the final angular speed is. That's this other thing I'm looking for. It gives me the alpha, 2.5 radians per second squared, and I'm looking at this after 4 seconds, right? So I fill the table out. Okay, now I'm going to come here and I need to pick an equation. Okay, so what equation doesn't have the angle in it, but does have the final angular velocity? And that's this one, of course, right? That first one we looked at. So I'm going to substitute in the values I know, the 5 and the 2.5 and the 4. I'm going to do a little bit of algebra, and we're sitting here at 15 radians per second, right? So this next one, what angle has the bit turned through? Okay, again, I now know this. I can pick any kinematic equation as long as it has the delta theta in it. I like this one a lot. So here's my change in angular displacement. So the initial, right, I substitute in the values I have. I run this into the calculator. And this is going to turn through 20, this unit is wrong. This is going to turn through 23.1 radians, not radians per second squared. That shouldn't be there. Pretend it's not there. Actually, here we go. Let's make it not be there. Voila. And look, it's not there. Hooray. Okay, so one more time. Okay, so this one, pause. Oh, wait. Oh, that just went backwards. Pause the video, right? Here's the question. Pause the video, work this out, and then check your work, okay? So a basketball player is balancing a spinning basketball on the top of his finger. The angular velocity of the ball slows from 18.5 radians per second to 14.1 radians per second, during which the angular displacement is 85.1 radians. Determine the time it takes for the ball to slow. Okay? Building my table. Don't know the alpha. Okay, so that's going to point me to this kinematic equation. Or you can pick a kinematic equation that will allow you to solve for alpha, and then you can use any of them, but that's extra work, so I do it. I'm going to substitute in the values I have. I'm going to solve for t, right? 5.22 seconds, okay? This is just like the linear kinematics. It's just in rotational terms, okay? So you need to think about this a little bit differently, but not that much differently, right? By the way, would this alpha be positive or negative? Is it in the same direction as the omega or opposite it? You're like, well, it's slowing down, so it must be an opposite alpha to the omegas. Okay. Well, some of you have probably been thinking, well, we kind of already have dealt with things going in a circle, right? We have circular motion, all the circular motion stuff, right? So as I look at the red dot and the blue dot as these things go around and around, where is the centripetal acceleration the greatest? So if I have a blue-headed kid and a red-headed kid on a which one of them has the greatest centripetal acceleration, right? And you know that centripetal acceleration is v squared over r, where this v is the tangential velocity, right? The blue one is going to be going faster, right, because it has a bigger radius. So, right, it's going to have the greatest centripetal acceleration, okay? Now, is that centripetal acceleration related to alpha? I mean, it is related to alpha, but it is not alpha by itself. So let's look at these two things, okay? By the way, the red-headed kid, the blue-headed kid, right, both the same. Do they have the same centripetal acceleration? No, they don't, right? It's the blue guy out here with the higher tangential velocity. Okay, so the further out, the fastest, right? Let's say I have a line of skaters, and they're all kind of skating around. This one has to go much faster if it wants to stay in line than this guy over here, okay? We already know this, right? We looked at arc length, right? That the arc length that's traced out is going to be equal to the change in the angle times the radius, right? We kind of established this in an earlier slide, okay? So what happens, all right, there's the arc length, there's the radius, right? Here's the arc length, here's the radius. Excuse me. Here's the change in angle, right? All of my variables are right there. So what happens if I divide both of these by time? Well, the arc length over the time becomes kind of the average tangential velocity. And the change in angle over the change in time, well, that's just omega. So you can think about the tangential velocity of any one of these people is their omega times the radius, right? Now remember that their angular velocity for all of these skaters is the same, right? Because the rate at which their angle is the same if they stay in a straight line. But I can figure out what their tangential velocity is by taking that omega and multiplying it by r, okay? So I've got this thing you're going to use all the time, bouncing back and forth between what is the angular velocity and the tangential velocity, okay? So back to the merry-go-round. Centripetal acceleration is this, but we know that tangential velocity, we just kind of thought through this, is also the radius times omega. So I can plug that in here, square both of these terms. Notice there's 2 r's on top, 1 r on bottom, so that divides out. So the centripetal acceleration is equal to omega squared r and, right, so the angular velocity squared times the radius, or you can calculate it with the tangential velocity squared over the radius, okay? And so in this animation, I have, let's start it over. I've got notice they all have positive omegas, but notice this red one starts slowing down, turns around. It must have a negative alpha. Blue has no alpha at all, so it's just cruising around at a constant angular velocity. Green has a positive alpha, so it's going to keep speeding up in this direction. Now red is speeding up in a backwards direction from blue, right? But this thing, if these were cars going around the racetrack, and I asked you about their centripetal acceleration, you could calculate it 2 ways. You could use angular terms to calculate it. You could use tangential terms to calculate it. And then once you have the centripetal acceleration, I could also ask you questions about whatever that centripetal force is, right? How much friction is there that's keeping the car going in a circle or whatever it is, right? Maybe it's like a can tied to a rope and you're spinning it around, right? Okay. So let's look at this new scenario to help us think a little bit about how to connect some of these principles, okay? So here's Jeff. He's riding on this cart. The cart's going 30 meters per second, and Jeff is running on top of the cart at 5 meters per second. So relative to the cart, Jeff is going 5 meters per second. But how fast does Greg see Jeff going? And if you're looking at this, you're like, well, okay, 30 meters and 5 meters per second, right? So according to Greg, Jeff is running at 35 meters per second, right? Well, what about this? What about this case? If the cart's going 5 meters per second to the right, but Jeff is running 5 meters per second to the left, well, what does Greg see? Well, and Greg's just see Jeff kind of standing still, and the cart's like sliding out from underneath him. And as soon as we run out of cart, Jeff's going to just drop down to the ground, right? So relative to the ground, Jeff isn't moving, okay? This idea is going to help us, okay? So here we go. Okay, now we're going to add some rotation. I got a car on a lift, okay? Pick this car up, and right now the car isn't moving. Velocity of the car is 0. But what happens if somebody's in there and starts pressing the gas, right? The wheel starts to turn, okay? And if I look at a particle on the outside edge of this wheel, the tangential velocity of that particle is just the omega, right? What is the angular velocity of the turning wheel times the radius of the wheel? That'll tell me how fast a single particle on the outer edge of the wheel, right? If this guy ran over some gum, how fast is that piece of gum going? Well, it's going this fast, the radius times omega, okay? And, right, that speed here, it's the same speed there because radius didn't change, right? Same speed as this thing goes whipping around, okay? Now, let's lower the car really slowly. Now remember, the car isn't moving, the dolly isn't moving. I'm just lowering the car. I don't know if you heard that. But as the car, right, if that wheel is spinning like crazy and then I bring the car in contact with the ground, it's going to spin out. It's going to skid out. You're going to get that, you know, as the tire grinds against the pavement, right? And this thing, the whole car is going to try and jump forward, right? Okay, so why are we even talking about this? Okay, well, to think about this question. How fast would I have to move the lift, right? So if I made this thing start going forward. So I'm going to move the lift. How fast would this need to be going so that when the car got down to the ground, if I'm still lowering the car, that I don't get the sound, that no spin out, right? How fast does this need to be going so that when this gets to the ground, it doesn't spin out? Okay, one way to think about this is I need the edge of the wheel, right? Think about Jeff, right? I need there to be no motion between the edge of the wheel and the ground. Okay? For Jeff, if the cart's going forward at 5 and Jeff's going backwards at 5, then Greg sees him standing still. If I want there to be no sound, I need this to be going forward just as fast as a particle on the edge is going backwards. Okay? So, what does the velocity of the cart need to be? Well, it needs to be r times omega. Okay? In order for this not to slip, in order for the edge of the wheel to have the same velocity as the rest of the car, I need the v of the cart to be r times omega. This is our key, class. This is the key. We call this the rolling condition, where the velocity of the car is going to be the same as the angular velocity of the wheels times the radius of the wheel. This is going to be so important. This is how I get to thinking about what the wheel is doing to what the car is doing. Now again, this is the rolling without slipping. There's no slipping of the tire, no skidding, none of that. Okay? So for our rolling conditions, velocity of the car is going to equal the radius of the car times omega, but I can apply that across the board. The change in the car's position for the rolling condition is going to be the same as the the change in the angle, as measured in radians, times the radius of the wheel. The acceleration of the car is going to be equal to the angular acceleration of the wheel times the radius of the wheel. Okay, so like a cool way to think about this is if I replace these tires with a huge tire, right? That thing's being turned by what do you call that stupid pin that connects the wheel to the car? The axle. That thing's being turned by the axle, so the alpha is going to be the same, but if I have a huge R, I'm going to get a bigger A, which you have to be careful of, right? If you put the wrong size tires on your car, you can like break your axle into a billion pieces. But if you put a donut on there, right? If you make the radius really small, you blow your tire out. Well, then that same alpha is going to give you a smaller acceleration. So, okay, I've given you a lot to think about, and we are going to practice this stuff a ton next time. So give the homework a swing. Remember that all of the work and practice you did in kinematics is going to play out here just the same. Build your tables, and if you need to make a bridge between what the wheel is doing and what the car is doing, this is your bridge. Okay, the rolling condition. Awesome. Okay. Thanks, everybody. Have a marvelous break, and I will see you in a week.